So now we can put these ideas together in the final decoding algorithm, the beam search algorithm for phrase-based models. So the input to this algorithm is a sentence, x1 through xn. For example, this might be a sentence in German. And in addition, we have a phrase-based model. So the phrase-based model consists of a lexicon, L. Remember, that consists of a very large set of German phrases paired with English phrases, for example. We have a language model, which I've called H. We have a distortion limit, little d. So for example, d is equal to 4. And we have a distortion parameter, eta. So given the input and the phrase-based model, we can define these functions ph of q and next q of p. Remember, ph is a function that takes a state as its input and returns the set of phrases that can follow that state. And next qp takes a state together with a phrase and returns the next state, the state formed by concatenating this phrase to this state q. So let's be concrete and assume we have an input sentence of length 7. So we have x1, x2 up to x7 as the input. And a key data structure is going to be this set of Qs. I'll use this capital Q for each Q, or beam. So I have Q0, Q1, Q2, and then right up to Q6 and Q7. And we'll see each of these Qs is going to contain states which are created during the search process. The initialization step is to set this first Q to contain a single element, little q0. Remember, little q0 was this initial state. It's going to be something like star, star, 1, 2, 3, 4, 5, 6, 7 zeros, and then position 0 and score 0. Okay, so we just have this initial state here. Okay, so the next thing we're going to do is go into a loop for I equals 0 to n minus 1. So we're initially going to start at q0, and we're going to move through each of these q's in turn. And what do we do for each value of I? The first thing we do is we look at every possible state in q sub I. So in this case, we would just look at the initial state. And then we explore every possible phrase that can follow this initial state. So we're going to look at all phrases P in pH of Q. So we might have things like 1, 2, must. It basically corresponds to the set of outgoing arcs here. 1, 3, sorry, that should be 1, 2, we must. 1, 3, we must. Also, maybe 3, 3, also. Okay, so we're going to have some set of phrases that could follow this initial state, and we're going to explore each one in turn. For each one of these possible phrases, we calculate the next state, call this q primed, and then we add that state to the appropriate q. So, for example, if we look at 1, 2, we must, we get the following state. We must 1, 1, 5 zeros, 2, and then some score minus 2.5. So this state is going to get added to one of these Qs. Which one does it get added to? It actually gets added to Q2, and that is because the number of words translated in this state, Q primed, is equal to 2. So Q2 is going to store a whole bunch of states with the one restriction that each bit string in these states has exactly 2 words translated. So the idea in these beam search algorithms is, in some sense, to group together states which have the same number of words translated. So that's what Q0 is. We have 0 words translated. Q1 has 1. Q2 has 2. Irrespective of position, we're grouping together states which have the same number of words translated. So if we look at these 3 phrases here, this phrase here, 1, 3, is going to lead to a member of Q3. So we're going to add some state to that. This one's going to add to Q1. And so in this first step, when we considered I equals 0, we considered the single state Q0, we consider all ways of extending it, and that's going to lead to a bunch of new states, Q primed, which are added to these later Qs. So notice we have this add function, we'll describe this in a moment, but intuitively this is just going to add some some state Q primed to Qi, critically where I is the length of Q primed. This is the number of words that have been translated in Q primed. Add is also going to take Q and P, the previous state and the phrase. That'll just be for some additional bookkeeping. Okay. So we actually move through these Qs one by one. So Q0 is going to take this one state and expand it in these various ways. Now I'm going to get to Q1, and I'm going to find one or more states in Q1. For each one, I'm going to go through the same process. I'm going to find all of the phrases that can follow this state. I'm going to concatenate them. I'm going to add entries later. So as you go through this, you're going to populate more and more states in these various Qs. Okay. Finally, we'll hit Q6. And we'll take off all of the states from this and populate. In this case, we can only populate Q7 from Q6. So we always pick up a state from an earlier Q and extend it by populating a state in a later Q. The final thing we do is we return the highest scoring state in Q sub n. So Q7 in this case. So we would have some set of states in here. Each one of them will have a score. And you simply return the highest scoring state in this set, in this Q, and that will correspond to the highest scoring translation found by this beam search process. In a very similar way to dynamic programming, back pointers can actually be used to trace back the steps in constructing that particular translation, and we thereby get the final translation. So let's just look at two functions which play a critical role here. One is this add function, which as we'll see is fairly simple. And secondly, we critically have a beam function. Okay, so actually when I said we take Q in out of each state Qi, so if we take Q0, Q1 is equal to some set of states, Q2 is equal to some set of states. If we're not careful, these sets will quickly grow exponentially in size. You can end up with a huge number of states because, as we said before, the number of possible states in these models is exponential in size. And so this beam function is actually going to only consider a small subset of the items in a particular queue and expand only that small subset, and that's going to make this whole thing efficient. Okay, so let's look at these two functions, beam and add. So here's the definition of add. Add takes a Q, capital Q, and a state Q primed and adds Q primed to Q. And remember, Q primed is equal to next Q and P. So this is just some record of the history that was used to create Q primed. The first thing we do is we check to see if there's something already in the set which is equal to our current state. Okay, so remember the equal function. So if I, for example, have something like the following, must also 1, 2, 3 minus 2.5. Okay, so maybe this is Q primed. This is the thing we're adding. And we have some existing state which looks extremely similar. In fact, it's equal under the definition of equal I gave earlier. So I should have had a position here as well, 3. Okay, so these two states are equal under the definition I showed you earlier because the two words, the bit string, and the last position, the final phrase, are all equal. The only thing which differs is the score. This step is going to be very similar to dynamic programming. If the two things are equal, we simply keep the highest scoring element because that records the highest scoring path to this particular state. And there's no reason to keep the lowest scoring path. Okay, so we do two things. We check if the score for the new thing being added is greater than the old score, and if so, we remove the old state and we add the new state. And we record the back pointers. So these back pointers are going to say I reach state Q primed by extending state Q with phrase P. Okay. Otherwise, if we don't find anything in the queue which is equal to the current state being added, we do the following. We simply add it, we add Q primed, and then we set the back pointer to set this record. Okay, so that's the add function. So basically we're just adding q prime to q, we're recording a back pointer, and we're being a little careful if we have multiple states which are equal but have different scores. We simply take the highest scoring of those states. The final function is this idea of beam. So beam q is going to be basically a subset of just the highest scoring items in q. How do we define that? Well, we say we have some set q, and it has a number of possible states, and each of these has a score. So let's write down a few scores here. And so on and so on. We first find the highest scoring state in the set, minus 1.8, for example. So maybe that's the highest score. And, sorry, that should be max, not argmax. Okay, so alpha star is the highest score for any state in the set. Beta is some beam width parameter which says, well, how far, so for example, we might take beta is equal to 5. And so then we subtract the beam, so minus 1.8 minus 5 is equal to minus 6.8. And we basically keep any states which have score greater than or equal to this and throw any other states away. So for example, a state with minus 100 would get thrown away, or a state with minus 25 would get thrown away. Okay, so beam is just going to keep all of those items within a certain tolerance of the highest scoring element in that queue. The intuition here is that we can sort of throw away some translations, even before they're complete, as being very suboptimal if they have low scores at this particular state. So let's just go back to this algorithm and see how these two functions are used. So remember, we go for I equals 0 right the way up to n minus 1. We only remove states which satisfy the beam condition. Okay, so we only remove high scoring states. At each point we extend that state, and then we call this add function. And this add function will actually throw away items where we have two states that are equal, but one has a higher score than the other.